You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Professor Jason Wright. Jason Wright is a professor of astronomy and astrophysics at Penn State and a member of the Center for Exoplanets and Habitable Worlds. He studies stars, their atmospheres, their activity and their planets, whilst also working on SETI. He is a project scientist for NEED, a PI of the Nexus for Exoplanet Systems Science, a co-PI of the Miniature Exoplanet Radial Velocity Array, and a member of the Habitable Zone Planet Finder team. You can learn more about his research on his blog. There's a link in the description, or by following him on Twitter at @astro_Wright.
Jason Wright, welcome back to the program.
Thanks again.
Now, Jason, we were just talking off air about some of the weird incidences that happened around the KSE 8462852 affair that one team actually, or two teams apparently, actually looked at it in laser and found something, and one ended up being an errant cosmic ray, and the other, I'm not sure what happened. Go into detail on that.
Yeah. When Tabby star became a sensation and everybody was interested in it for the SETI angle, it naturally got targeted by all the SETI programs because, that's how it became famous, is that we tried to use the Green Bank telescope to see if there were any radio signals coming from it. So there are two projects to find laser signals that might come from stars that work in different ways. One is based at UC Berkeley through the Breakthrough Listen project, and they're looking for continuous wave lasers. So someone shining a laser all the time. And it turns out, it doesn't take that much energy to outshine a star if you use a laser and you're only concerned about outshining the star at that one wavelength, that one color. And so that's what they look for, is that. And they looked at lots of targets. They looked at Tabby star, of course, and then when they went to go publish their results and see if they had anything interesting, they wanted to publish their very best candidate as an example of what they were looking for. And wouldn't you know it, the very best candidate they had was Tabby star. In this case, it turned out that what they had found was a cosmic ray. So this is a misnomer. It means an energetic particle, a product of radioactive decay. And so basically, our detectors are so sensitive that even the trace amounts of uranium, let's say, in the walls of these observatories will occasionally give off a particle. And that particle will hit the CCD and you'll detect it. And it'll be really bright and it'll be really obvious, and it'll often look like a laser line. And so we call these things cosmic rays because they have similar properties to the energetic particles called cosmic rays that come from space, even though they're actually coming from the walls. There's kind of a joke in astronomy that if you see something really weird that doesn't make any sense, you just ascribe it to cosmic rays. A cosmic ray hit the detector. Or maybe a cosmic ray went into my computer and it messed up the calculation, and that's why that thing didn't work. And you run it again and it never happens again. The running gag. Something weird happens, something goes bump in the night, doesn't make sense, never happens again, cosmic ray.
Now, speaking of uranium in the walls, uranium in a star, we have a candidate Technosignature, and it is a Przybylski star, which seems to show some very, very strange elements within it, including apparently uranium and upwards, according to one study. If that is indeed there, is this the closest we have come to saying that could be due to an alien civilization's activities?
Yeah, so Przybylski star is one of my favorite astrophysical enigmas. It's just so neat. It belongs to a very strange class of star, at least we think it does. It's really anomalous, where it's very slowly rotating and they have very strong magnetic fields. And apparently this combination of the temperature of the star and the strong magnetic fields causes the different elements in the atmosphere to segregate and form layers. So all of the, let's say, I don't know, we'll pick something like nickel or something in the atmosphere of the star will get concentrated at one layer. And if that layer is deep enough that you can't see the layer, then you won't see any nickel in the star at all. Whereas another element in the star, like, I don't know, molybdenum or something like that, might all concentrate much higher in the atmosphere where you can see it. And then you'll see an amazing amount of molybdenum, like much more than you should ever have any right to see in any star, because you've got all of the atmosphere's molybdenum right there where you can see it in that thin layer. These are called chemically peculiar stars, AP stars, and they really have strange abundance patterns. But Przybylski's star is just totally off the charts. It has so many spectral signatures of so many elements, so many transitions of so many elements, that we actually have a very hard time identifying any of them. And this is because the heavier elements on the periodic table have lots of different ways that their electrons can transition. They provide many different wavelengths of light where they can absorb. So if you put enough of this stuff, enough of these heavy elements in the way, all those lines will overlap, and it's just a complete mess, and you can't identify anything. Sort of, I guess, like, trying to pick out, one piece of music when many, many pieces of music are playing. If you just have enough of them, there's just too many, and you can't tell them apart. So people have heroically tried to identify these lines. One problem is that we don't actually know at exactly what wavelengths a lot of the heavier elements absorb, just because no one cares enough to go measure very carefully. But the one study that tried the hardest at this and really did their best to identify the lines concluded that they had confident detections of transuranic elements, of actinides. And this should not be possible, because the elements they were discovering have half-lives of like 100 years. Or in some cases, just less than a year. And such elements can't exist in nature because they decay away far too quickly. And so it's impossible. It has to be a line misidentification, which is not surprising because we can't identify any of the lines. So it's clearly just a mistake. But there does exist the possibility that, maybe it's technologically generated. So, why would there be technologically generated short-lived radioisotopes in this star? The original proposal for this goes back, as far as I can tell, to Carl Sagan and Shklovsky, it goes back to Shklovsky and Drake, I think, who apparently made the suggestion that if you wanted to let people know you were out there, you could put something, like plutonium in a star, or technetium in a star, and then anyone who noticed it there would know it had to have been put there. They called this salting stars. And so that could be a really interesting beacon, and very energy efficient too. You just have to put the material in there, and then the star has it, and it'll shine, and everyone will be able to detect it for, as long as the star's around. So it could be a beacon. The second idea is that it might be a repository for fissile waste. So this was a suggestion of the times, made around 1980, when disposal of fissile waste was a real problem. I mean, it's still a real problem, but when it was a really salient problem on a lot of people's minds, it's gone away for some reason, that, you could just get rid of it by dumping it onto the sun or something like that. Now that's an absolutely terrible idea. You should, the last thing we should be doing with our nuclear waste is putting it on gigantic towers of rocket fuel and lighting them. It's far too dangerous. Who knows? Maybe someone's doing that, dumping a lot of fissile waste into the star. It seems a little far-fetched to me, but the suggestion's out there, so it's entertaining to think about.
Now, what of technetium with this star?
I don't know if it exhibits technetium. I think actually technetium is observed in space. This isn't really my field, but I think it is actually produced in supernova, I guess, and so sometimes you do see it, perhaps. But you don't find it on Earth because it's all decayed away in the 5 billion years that Earth has come along. But like I said with this star, it's hard to identify anything. The elements they identify are all transuranics, like actinium and einsteinium and these things.
Pretty hard elements to arrive at. Now, astrophysically, say that stuff is actually in there.
Yeah.
Is there a special circumstance where it could be being produced on a continuous basis, say bombardment of a neutron star or something like that?
There was a paper that suggested that if there were a nearby neutron star, you could somehow do the chemical nuclear reactions necessary to generate it. The problem is there's no neutron star around it. I mean, it's a clever idea, but this star doesn't have any companions. Those lines that we see, they're always at the same frequency. We see them just constantly at the same frequency. So that means there's no Doppler shift, no changing Doppler shift, which means nothing's orbiting the star. We know that to very high precision. So there's no neutron star. Actually, my favorite suggestion, which is really clever, is that they are the decay products, the daughter products of a reservoir of some other element that is more slowly decaying. So the idea is that there is some stable element out in an island of stabilities, the physicists call it, that we've never synthesized, that we've never made elements heavy enough to notice that they're stable for, who knows, thousands, millions of years. It's possible. Most calculations say all of the elements up there are extremely unstable, but some suggest that there might be an island of stability. So if for whatever reason this star has a lot of that element, and we don't have any of it on Earth, so it's unclear why they'd have it, but we don't. But okay, let's just say a special supernova enriched it or something. Then this element might be in the atmosphere, stratified, as this class of star does, and slowly decaying. And that could be the reservoir that's generating all of these daughter decay products all the way down as it decays down to uranium or something like that. I really like that idea because it means that in principle, if you can confirm these elements are real, and if you can confirm are really there, and you can confirm that they appear in the appropriate quantities to be a decay chain, that you would have detected or at least inferred the existence of a new chemical element in space. And I'm pretty sure the last and only time that's ever happened was with helium. And it would be the first new element found in nature in a long time. So that would be pretty cool.
Well, presumably an entire group of all the way up to this island of stability, you would have, above stuff that we've synthesized so far anyway.
No, that's true. We know that they can exist, but yes, you will have discovered them. That's right. You will have discovered them, and maybe you could tell from the lines in the spectrum which ones they were and actually do some spectroscopy of them. That would be pretty cool. I like that idea. It's a really obscure idea, but it's a lot of fun to think about.
It is, and it's interesting because, I don't know that these elements that they've synthesized more recently, muscovium and all those, that they even last long enough to get a spectra off of it.
No, exactly. That's right. And so we wouldn't even know. You'd have to presumably do the quantum mechanical calculation to figure out what the energy levels are. And I'm not a quantum chemist, so I don't know how hard that is. But my understanding is it's very hard and maybe beyond our capabilities right now.
Yeah, I tend to think so. Just synthesizing them is hard enough, and wondering about what kind of chemistry could go on with such an element is just all speculative. Now, other technosignatures. Another one comes to mind, the red spiral.
Oh, yes.
Give us an overview of that.
I'm not sure it's a technosignature, but it's a really neat little story. There's a website called Zooniverse, where citizen scientists can go and help astronomers with gigantic data sets that are just too big for them to work with. And one of the projects was called Galaxy Zoo. And so the idea was that there were these large all-sky surveys that just took images of the entire sky. And they wanted to do old school galaxy morphological classification, where you say, okay, that's a spiral galaxy, that's an elliptical galaxy, and that's a lenticular galaxy, that's not a galaxy, that's two galaxies. And it's very hard to get a computer to be able to do that without a training set. You have to give it an enormous set where you say, all of these are this, all of these are that, all of these are that, now go do the rest. And so that's what Galaxy Zoo was for, is that all these volunteers learned about the kinds of galaxies and then categorized just thousands and thousands and thousands of these things. It was extremely productive and useful scientific endeavor. But one of the cool things they found was a rare class of galaxy that was not in any of the classification schemes, and that are the red spirals. So the two basic kinds of galaxy are elliptical galaxies and spiral galaxies. And spiral galaxies, they look like pinwheels, like the Milky Way or Andromeda or M51 or something like that. And they've got the great spiral arms, and all along those spiral arms are bright blue stars. And that's because the spiral arms are sites of star formation, and when you form a lot of stars at once, some of them have very high mass. High mass stars are extremely bright. They outshine all of the others, even though they're pretty rare. And they're very blue because they're very hot. And so it's characteristic of a spiral galaxy to have all these blue stars. And then elliptical galaxies generally have very little dust and star formation going on. They're often the products of spiral galaxies that have merged and just burnt up all of their dust and gas as stars and are done forming stars. And so they haven't had any stars form in the last, say, hundreds of millions or billions of years. And as a result, they don't have any blue stars, or they have very, very few blue stars, and for different reasons. And so they are dominated by the light of the red giant stars, which are stars maybe like the sun that have been around for 10 billion years and are now red giants. So the general rule is that elliptical galaxies are red, spiral galaxies are blue. And what the galaxies do people found were red spirals. They looked like spiral galaxies, but they didn't have any blue stars, and that's really strange. And so the red spirals, as they came to be known, emerged out of that project, and they're an interesting anomaly. The way it's usually explained is that in the past they had a huge burst of star formation, and that all of the stars from that burst, the blue ones are all gone, they went supernova, but the lower mass stars are now red giants. And so the idea is that they do still have star formation. They still do have blue stars. They just have an unusually large number of red giants, and that's why they appear red. And, that makes sense. I think what you mean by technosignature is that there are ideas that if you're a galaxy-spanning civilization and you have ambitions to last a very long time in the galaxy and minimize supernova explosions or worse that might, cause a lot of trouble, that you would somehow suppress high mass star formation and prevent those blue stars from ever forming in your galaxy. And so this galactic engineering, essentially, to make it safe for the species that fills it. And so that might look like a red spiral. And so I think that's what you mean, that red spirals could actually be a technosignature.
So in that regard, so if you're looking at galaxies and you see a galaxy that is very reddened and has a whole lot of excess infrared as though it's full of Dyson spheres, then you might be getting into territory where you can say that is unambiguous, right?
No, I wouldn't say unambiguous. If I saw, it'd be very interesting, right? It would satisfy it would look a lot like proposed technosignatures where, as you say, maybe lots of Dyson spheres, maybe suppress the blue stars. That might be what it looked like. But it would also be consistent with something that had a burst of star formation in the past. That's why it's red, and still has a lot of dust and maybe has a lot of star formation also right now. Maybe it just had a merger, so that would also give you a lot of excess heat. What you'd want to do is look very carefully at the morphology of the galaxy and just see where the infrared emission is coming from. If it's coming from the spiral arms and the sites of star formation, well, that's all it is. It's no big deal. But if it's coming from all of the stars in the whole galaxy, if it's not clumpy the way that dust is, that would be very suspicious. So it would be anomalous to see infrared excess in a red spiral. And in fact, we looked for that. In the GHAT survey, we checked all of the red spirals just to see if any of them had infrared excesses. And indeed, we found a very small number of them had too much infrared radiation, which was pretty strange. And then we wanted to check to see if maybe there are some reasons why that might happen involving ultraviolet light or them being edge on, and we checked that, and those didn't pan out either. And so we think those 4 or 5 galaxies we identified must have some very strange star formation histories to be red and have infrared excesses and have the ultraviolet flux that they do. So we did flag those as interesting anomalies that kind of fit what we were looking for. They're distant and hard to study, and like I say, there's a good there are reasonable families of natural explanations for them. So no, I don't think it's unambiguous.
Now, what about a distance to those galaxies? Because eventually you're looking out so far that there just wouldn't have been time for a civilization to form up in that galaxy from your perspective as seeing it.
Oh yeah, these aren't that far away. These aren't at cosmological distances. And so the light we're seeing left those galaxies when the universe was not very much younger than it is today.
Now, other technosignatures. I think the most weirdest one I've heard of lately is Roger Penrose saying, well, maybe you could send a message from a previous universe by encoding it in the cosmic background radiation. Do you think we should take that step? Is that a step too far?
I'm out of field here. Roger's a brilliant guy with a lot of amazing ideas. I guess I would say that there are a lot of things that have to go right for that prediction to pan out. There have to be other universes. They have to be connected in some way that you can send information from one to the other. I'm not even sure what that would be involved. But also, I mean, if that information is, let's say, encoded in the cosmic microwave background, there's not much information there. Like, the whole cosmic microwave background map is just, it's not that much information. So I don't know how complex such a message could be and still be decodable. Yeah, I'm not going to argue with Roger, but I'm not sure how that would work.
Now, out of all of the technosignatures that you are aware of, potential technosignatures, what's your favorite? What's the one that really fires your imagination the most?
Fires my imagination the most. Well, I like infrared excess waste heat, looking for the inevitable heat that comes from technology's use of energy. Because it could be anything. It requires the least imagination or supposition about what it is they are doing. So I like that. I also am partial to that because that's what I look for, because that's closest to my wheelhouse as an astronomer. I'm not a radio astronomer. I don't build hardware. I don't work with fast electronics and things like that. And so that's the one that I can most easily look for. And so that's the one that I work on. But that's not to say I think it's the most likely one to pan out. I really don't know which technosignature will be the most obvious.
Now, could it be something, we look at, short terms with technosignatures. You either see the Dyson sphere or you don't. But there are also some that are much more long term. So say you're looking at exoplanets and you're doing several centuries of study of Earth-like exoplanets. And all of a sudden you see, or actually let's frame it like this. Aliens are looking at us and all of a sudden Mars becomes habitable again. So you detect terraformers. Now, is that perhaps a more viable way of detecting an alien civilization?
No, I don't think. To terraform a planet would take a very long time. And if it didn't take a very long time, you're unlikely to see it happen. This is the L in the Drake equation, that if you want to detect something, your probability of detecting it, or the number of them that there are to detect, is proportional to how long the technosignature lasts. So if you want to see something change over the course of 10 years, like go from uninhabitable to habitable or something like that, then you're looking for something that took 10 years out of, the age of the universe. And so it's very unlikely that you would just have happened to catch that planet at the moment something like that happened. People have also proposed, for instance, looking for, the evidence of, interplanetary warfare or a planet destroying itself, like Praxis or something like that. But again, those are very brief. If something only takes a short while to happen, it must be happening all the time, or you're very unlikely to have caught it. However, things like terraforming are definitely the kind of thing that you might infer technology for if you have some reason to suspect that a planet has been terraformed. So people have suggested looking for habitable planets outside of the habitable zone. Like, how is it that planet still has that atmosphere at that distance from the star? That shouldn't be possible. Perhaps there's some geoengineering going on. Or let's say you have 3 planets in the habitable zone of some star, and all of them have identical atmospheric signatures. 3 planets, different sizes, different distances from the star, identical atmospheres. That would also suggest terraforming, right? Because you would not expect 3 totally different planets with different insulations to end up in the same way. So I think that's a cool idea for a technosignature.
Yeah, and one that we're getting pretty close to being able to look for that now with James Webb going up and all that.
Yeah, I hope so. It's going to be very hard. It's going to be very, very hard to study terrestrial atmospheres, even with James Webb.
Yeah.
I hope it works.
Well, we're going to be limited to close, maybe we can look at Proxima b or something, but
yeah,
characterizing atmospheres is only just barely now, something that we can start to talk about. But once we do, if you saw, like you said, 3 planets with the same atmospheres, and if it got really interesting and 2 of those planets had CFCs, because that's an excellent greenhouse gas, so you could terraform a world with it, then you're outside of ambiguity at that point, which ambiguity has always been the plague of SETI. So
well, no, I don't think ambiguity's been the plague. Radio and laser SETI does not struggle with ambiguity. I mean, it can. If they go looking for things other than the sort of canonical narrowband radio signal or the laser, the pulsed laser, they might go looking for more ambiguous technosignatures. But, if you see a narrowband radio signal from space and you confirm it with another instrument, you're done. You win. There's no ambiguity. You've discovered life elsewhere in the universe. But I hear what you're saying.
Unless it fails to repeat because we picked up such a signal.
Well, that's why I said if you confirm it. It's got to be confirmable. You have to be able to know that it wasn't a cosmic ray.
Which is the maddening thing about the WOW signal. It definitely wasn't a cosmic ray.
Well, I don't know what the WOW signal was. Yeah, I mean, it would be, and again, this kind of goes back to our rate arguments. If things like the WOW signal were common, then someone would have seen something like it at some point since then. But it still remains this singular event, more powerful and stranger than anything we've seen. If it really was an alien signal from space, then we were extremely fortunate to catch it because it's apparently not a very common phenomenon. And yeah, and it's also frustrating because if it never repeats, then there's no way to know that it wasn't just a cosmic ray or something like that. Now, that said, Bob Gray has pointed out that if the WOW source is repeating all the time, we would barely know it because we don't know exactly where that telescope was pointed. I mean, we know where it was pointed, but it was a big beam, so we don't know exactly where on the sky it came from. And that region of the sky has not been thoroughly searched at those wavelengths for very long. He estimates that we've probably spent something like 24 hours of total integration time staring at that part of the sky, that entire part of the sky, look and sensitive at those wavelengths. And so it could be, for all we know, blinking at us once every 24 hours, and we still wouldn't know.
Well, he would be the one that looked at it for most of those 24 hours, I would imagine.
Yes, that's how he knows the number.
Yes. So say we get to this point where we find a technosignature. Then we get to have the debate on should we beam a message to it? What's your take on METI?
Okay, so these are two different questions. So one question is, once we detect something, should we try to get its attention? The other is, should we be broadcasting deliberately now in an attempt to elicit a response? To see if anything's out there. And that's what I think we normally think of in terms of METI. I don't think we should, because I don't think it's likely to work. I know most people say I don't think we should because I'm worried it will work and they're going to come eat us or something like that. My opinion is that these broadcasts are far too weak, they're far too transient to matter. I mean, imagine if there were a civilization out there trying to get our attention and they, blasted in our general direction for an hour. Unless we just happened during that hour to have a radio telescope pointed at the right frequency at that source during that 1 hour out of 5 billion years or something like that, it's not going to make any difference. We're not going to catch it. It needs to be something sustained for an extremely long time before it's going to work and get someone's attention. I think things like the Arecibo message are valuable because they remind us how sensitive we are to radio signals at interstellar distances. It gets us thinking about our place in the universe. It gets us thinking about SETI. It gets us thinking about what would happen if we were to make contact. But I don't think they're useful because they have any chance of actually getting attention.
I sort of like the Arecibo signal for another reason, because if in thousands of years as it propagates out, someone sees it, it's going to be their WOW signal.
There you go. I do enjoy that symmetry. That's really nice.
Yes. That's when you confuse the aliens rather than contact them. Now, to switch gears, you wrote another paper that fascinated me because the implication of it is that if you did detect some kind of an alien artifact or something like that in the solar system, you may not be able to prove that it's even alien.
Exactly.
Prior indigenous technological civilizations. Give us an overview of that paper.
Yeah, prior indigenous technological species. Yeah, a few years ago, my mind was blown when, and I don't even remember how the idea came, but it was. I know that one of the seeds was thinking about Gavin Schmidt and Adam Frank's work, asking about whether we could rule out a prior technological species on the Earth. And so, whimsically, you would say, how do we know the dinosaurs didn't have cell phones? How do we know? And you think, oh, well, that's silly. We'd see it in the fossil record. But no, the fossil record is extraordinarily incomplete. I mean, out of, millions or billions of dinosaurs that walked the earth, we have fossils of a few. We really don't know what was around then. Only certain things get fossilized. So they went and they were thinking about the Anthropocene, this idea that that humanity's impact on Earth is now so indelible and so significant that it's worthy of a geological stratum, a name. And so there are these eons and epochs in Earth's history where things changed, and the rock, you can see it in the rock layers. Something was different then. And the argument of the Anthropocene is that we've already done so much work, and we will continue to do so much work to alter the geological layer that we're putting down, that geologists 100 million years from now, going down through the rocks, will be able to say, look, that's where it started, and tell that we were here. And Frank and Schmidt don't dispute that. They say that's true. But given enough time, it won't obviously be technological. Like, something was different then, but you'd be hard pressed to prove that it was technologically different. There are other things that might have been able to do it. And it's surprising how much of our technology will vanish and just not be around, and certainly not be recognizably technological, in just 100,000 years. And they argued that after 1 million or 2 years, there'd be no way to know it's technological at all. And so, in fact, if the dinosaurs had cell phones, we would not know it, because, we wouldn't see the cell phones, and all of the other stuff they did would just be another layer that we would misinterpret. So building on that, I was thinking, well, this could be true everywhere, that if we go and we look at Mars and it seems dead, but we forget how recently it was just understood that Mars had life, had cities and canals and all of that stuff. I mean, 100 years ago, there were respectable scientists who thought Mars probably had life, and even intelligent life. And we got the pictures from the Mariner probes back, and it was just desert, and there was nothing there. And somehow the needle swung all the way to the other side, from probably or maybe has life to definitely never had life in its entire history. And there was no evidence for that. We've never had evidence that lets us go back just what's on the surface of Mars today in terms of life, or even technological life. And so I started thinking, maybe Mars did have cities. It wouldn't take that much time for them to be gone. Maybe Venus had cities, and then the global greenhouse effects has just completely wiped them out and they're gone. Maybe Earth has had many technological species in the past. And so if that's true, then if we, as you say, find an artifact in the solar system, the usual idea is that must have been deposited here by some visitor from interstellar space. But given that Earth has life and it's right there, isn't it more likely that Earth life put it there at some previous spacefaring phase of its history? And I don't know if that's more likely, but it's interesting, I think, that is somehow, to most people, seems like a ridiculous idea, even though we have no evidence for it one way or another.
I think that's interesting, because Venus would be an extreme example of this, because number one, that planet apparently had liquid water for a very, very long time, up until, geologically speaking, relatively recently, before it went all crazy. But the thing is, that planet also is even worse than Earth. It apparently cracks open and resurfaces, it completely resurfaces itself, which would completely eradicate any evidence of anything ever having been there.
That's right. If Venus has had a resurfacing, and I'm not sure it's certain that it has, but I know that is a common interpretation of its geology. That's right. Then all evidence of everything that was there is completely gone. It's been totally folded into the mantle, and yeah, you'll never know anything about it.
Now, with Earth, of course, I mean, people don't really realize just how active this planet is in destroying its surface. I mean, it will grind over time entire continents underneath a plate and, basically melt it down. So the vast majority of the history, as you say, of this planet, the fossil record is just not there.
I think it's actually mostly life and erosion. But yeah, your point is well taken. I mean, there are the plates that subduct under the oceans and stuff. We do have rocks that are billions of years old, and a lot of the Earth's surface is billions of years old. But I think people also, as you say, they don't realize how quickly life just destroys everything on its surface. Like if we all vanished, how long would it take before our technology was, not visible anywhere? It's not very long. I mean, if you do special things like build a gigantic pyramid of rock in the middle of a desert, that'll last thousands of years. But almost anywhere else, it's going to go away pretty quickly. And yes, certainly over geological timescales where earthquakes and eventually subduction for some parts of the Earth, yeah, it'll just go away. So deep time is really, really deep. And what seems very permanent now is not on a geological timescale. I agree.
Now, what of Mars? Say this might have happened, hypothetically speaking, on Mars. It probably would last longer, wouldn't it? I mean, say you have a giant piece of rebar concrete, and it gets buried on Mars 50 million years ago. Is it still going to be there in that environment?
Yeah, I don't know the answer to that question, but I would guess that if you have rebar on Mars, that some biological entity made the rebar, which means you've got life like you have life on Earth. You have a biosphere. And I think that the biosphere would destroy the rebar pretty quickly.
Yeah, the rebar, definitely. The concrete, though, I'm not so sure. Yeah.
Or the concrete. I mean, it's just silicates. So if it buried, yeah, I don't know. Yeah, I don't know enough about it. I mean, if it's on the surface, it'll get sandblasted on current Mars, but that also means it'll get buried. So I don't know how long concrete lasts. Yeah, it's a good question.
It could. It also, I guess, conceivably, there's a case of a quarry, I think in Sweden, where they found what appears to be fossilized meteorites, where the traces of the meteorite remained in the sediment, like iridium and things like that. But most of the silicates are gone and it's been replaced. So one wonders if that could happen with an artifact.
Yeah, I'm sure. I mean, you think about lichens, right? And all they need is sunlight and a rock, and they'll, give them enough time, and they'll just eat the rock.
That's true.
It's a long time. Although, with rocks, I suspect erosion is faster. Yeah, it wouldn't surprise me if bacteria are also an important player. So I guess that's the paradox, that if you've got the technology and it's indigenous technology, then the indigenous life, if it's anything like Earth life, is not going to let it last for very long. So the main thing is if it were deposited there, if it were like a remote base or something like that, like Elon Musk wants to build on Mars or something like that, if we set something like that up, maybe like the Antarctic station that we have, how long does it last? And yeah, the sand's going to get it pretty quick, but then it'll get buried. And after it gets buried, you don't have you don't have much in the way of Mars quakes. You're not gonna have sand blasting it anymore. Maybe you got to worry about meteorite impacts. I don't know.
Yeah, I mean, or asteroid impacts for that matter. If you live long enough in a star system, you're eventually going to get hit. Unless you do something about it.
That's right.
Now, what implications does this have on searching for extraterrestrial life? Because if you had a prior technological civilization on here or Mars or Venus, and they left and decided, we're going to go out to the Oort cloud because we can compute more efficiently because it's colder or something like that, then even if you got evidence, an artifact of them or something like that, you could never say that they were actually alien because it's just Earth life. And even if they were genetically very different, well, maybe they have full command of their genetics and customized it. So you can never actually say at a certain distance that something is unequivocally alien.
It's true. You can't prove a separate genesis. You can't prove a separate abiogenesis event just from that artifact. I mean, some people would go farther, though, and say that even if we find definitively extraterrestrial life, maybe that radio signal from a distant star, well, maybe the origin of life on Earth is common to the life that was on that star. Maybe that was Earth life that went over there, or maybe the panspermia hypothesis is valid and someone seeded both places. So, the separate origins is always going to be a puzzle unless they know the answer and they tell us. But that seems far-fetched to me, but maybe.
But then you have to trust them.
That's true. They could be just feeding us a line.
This is actually one of the reasons I'm more actually interested in microbial life in the universe, because there you don't really have that kind of possibility of subterfuge. It's either related to us or it's not. So you.
Oh, you mean if you find it in the solar system, then you can check genetics.
Yeah, if you find it, if you find it at Europa and you look at the genetics and you're like, there is just no commonality at all, then you can say, okay, the universe teems with life.
I would not be surprised if in a couple thousand years, the humans on Europa managed to stock the subterranean ocean with all sorts of genetically modified fish that can live in Europa. And it could be a completely synthetic life form they've designed to be there. I mean, we're already talking about generating synthetic life here on Earth. And so, give us thousands of years, and I bet we'll have lots of synthetic life that has no lineage with any other life on Earth, and perhaps we'll build it exactly because it thrives in space. So I don't know.
And maybe it'll even exhibit convergent evolution artificially. So it looks like a shark. So you have a giant artificial European space shark.
That's right.
And
it turns out we made it.
Which is now again, this goes back to the thing that's better than aliens. If we can do something like that, that's more interesting than an alien civilization.
Yeah.
Which honestly, I do wonder, in regards to biosignatures, if we don't really have a better chance of understanding abiogenesis actually from a test tube. In other words, the alien life comes out of a test tube.
Yeah.
From the biologist looking into the origins of life, which seems like that's probably going to happen within our lifetime. So even if we don't find a biosignature or a technosignature, if it looks like the chemistry of abiogenesis is easy, then we can still look out there and say, yep, it's everywhere, at least microbial life.
Yeah, it's possible. My personal suspicion, and this is an uninformed suspicion, is that abiogenesis is hard. It might be very common. It might have happened in the blink of a geological eye on early Earth. That's possible. But the blink of a geological eye might mean a million years of a lot of things going just right. And it's possible that there's no substitute for just waiting, that these reactions are extremely unlikely, that you need just the right foam bubbles on a tide pool, this and that, and that there's no way to hurry it up and simplify it and do it in the lab. It's possible that we'll always just be wondering, well, this is probably how it happened, we think. I don't know.
Well, the one interesting thing about that, though, is that however it happened, it seemed to happen just as soon as it was possible in this world.
That is consistent with the evidence, but I've heard it persuasively argued that it's not that ironclad, that the dates on those rocks and the evidence for life in those rocks, which is isotopic, it's not even in the rocks, it's in these little minerals in the rocks, have particular isotopic ratios that are consistent with life. I think it's an ambiguous biosignature, and so it's certainly possible, like I said, that life arose as soon as we had water on the surface. But it's also possible, this is hard, that we've overinterpreted that evidence, and it actually took, let's say, I don't know, that it took 100 million years. I don't know the numbers. I'm not a geologist. But that it was actually on the long side. And if that's the case, then maybe it was a rare event on Earth.
But, the universe does not like uniqueness, so there are probably other examples.
No. We're not unique. That's true. Life is not unique to Earth. I
think we can confidently say that. Now, what do you think about civilizations, though? Do you think, your gut feeling, are civilizations relatively common, or is intelligence just very, very rare? And that explains the Fermi paradox.
Well, the question is, what's the hard step? It's possible that Earth had many hard steps, from abiogenesis to, cells to multicellular life, and then from multicellular life to life with they can be social or can use tools. I think Earth has had many examples of intelligent tool-using species and social species, right? We, as far as we know, are the only one that is social and tool-using and language-using and has all of the things that we do that give us so much technology. But we have plenty of examples of very intelligent species here on Earth today, octopuses and dolphins, plenty of social species, plenty of tool-using species. So I'm kind of surprised given that we're the very first to figure out technology, and I bet there have been species that found technology and maybe even found, fire and built things. I mean, beavers build dams and stuff, but beyond just instinct, but really solving problems and developing new technologies. I'd be surprised if we were the first on Earth. I would not be surprised if we're the first to do geoengineering and build big cities and rockets. That seems right that we are the first to have done that, but again, we don't actually have evidence. So that's it for me. If life, multicellular life with neurological capabilities like animals, is common, then I think technological species are common. So I think we're either going to find, we're not going to find lots of forest moons and things like that and not find technology, I think, with at least some of them.
Now, my last question for you relates to yet another paper. What is the aurora effect?
The aurora effect, yes. So this was Adam Frank's idea, based on a novel by Kim Stanley Robinson. The aurora effect is that not every habitable planet is habitable. Wait, oh shoot, I can't remember how he phrases it. But it's based on a novel where humans go to a planet and it seems like a great place to live, but it turns out that because of the stuff already living there, it's not. You can't live there. You can't also be there. And maybe the aliens from War of the Worlds discovered that about Earth. It looked like a great place to be, but it turned out that they just couldn't live here. So the reason this came up in this paper is that we wanted to understand how severe the Fermi paradox is. Specifically, Fermi's original articulation, which has nothing to do with SETI, asking why aliens aren't here in the solar system today, aren't obviously here in the solar system today. And the argument is just a crossing time argument, that even with today's technology, we can create spacecraft that, given enough time, can get to nearby stars and even cross the galaxy. Now, enough time means hundreds of thousands or millions or tens of millions of years, but that's fine. Those time scales are short compared to the age of the galaxy. So there's been time, if there have been other technological species, for them to have populated and settled the entire galaxy, if they were so inclined. So the question is, why haven't they? Or if they have, why don't we notice them here in the solar system? So one piece of the puzzle in the paper was, well, how do we know they haven't? What's our evidence horizon? And so based on his work with Gavin Schmidt, they said, all right, let's be generous and say 10 million years, that if they were here in the last 10 million years, we would have noticed. So then the question is, well, how often do they visit? So we ran some models of how long it would take to visit all the stars in the galaxy. And we don't know how often they would launch ships or how fast their ships are or anything like that. So we just parameterized it all and said, well, if the ships are typically this fast, if this fraction of stars are the sorts of places that they could settle and launch new ships from. And we tuned those parameters and just saw under what circumstances you would expect a star like the sun to have been visited in the past 10 million years, and under which circumstances 10 million years is a perfectly reasonable time to go without being visited. And so that helped us put constraints on how ubiquitous space travel must be among technological species in the Milky Way.
And do you expect it is ubiquitous? Because, space travel is also very hard.
It's not very hard. We do it. It took us, I'm serious. From the development of flight to the first interstellar probes was decades, just a few decades. So I don't think it's hard in that sense. It's hard in the sense that I think the hardest part of the problem of going to nearby stars is building something that will last long enough to get there. The rockets aren't the hard part. The hard part is, how do you build something that very far from a star will still be going and useful in 100,000 years? And that we don't understand. We do not understand how to build machines that last anything like that amount of time. So it would presumably have to be something that can repair itself, perhaps. It's a colony ship and it's people that are doing the repairing. I don't know, but that's the hard part. But it also doesn't feel so hard that we'll never do it on a cosmic timescale to me. We already can draw the outlines of how such a thing would work. Hollow out an asteroid, use its mass for propellant, off you go. So the fact that we can outline and describe it, and it doesn't violate any laws of physics to build a slow ship, suggests to me that it's actually not that hard if we could basically do it.
Well, and you can also reframe it, because if you build, say, hollowing out an asteroid, and you build a gigantic generational ship, eventually it can be so extensive that it is a world. So
Right.
as you space travel, you're just going about life on a world, more or less.
That's right. Exactly. Right. If it's spinning, you've got your gravity, and if it's big enough, it's got enough propellant to go, kind of fast. The asteroid gives you plenty of shielding from everything on the outside. You've got all the raw materials you need to keep it going. I guess, I don't know, you do fusion or fission or something for your energy. And that's right. If it's a generation ship, then it's its own world. But the other thing is, by the time it arrives, they're no longer really Earthlings, right? I mean, they would be our genetic descendants. But 100,000 years of your own culture, with Earth just getting ever farther away, you can communicate with Earth and try to maintain that culture. So, as long as stuff on Earth is still transmitting, you can still receive and answer and interact. But when you're that disconnected, you're going to be your own thing by the time you get there. So I guess they're Earthlings biologically, but culturally, they'll just be doing their own thing when they finally get there.
Yeah, they might not even know that they were from this world or anything like that.
Yeah. I mean, Earth would only be a couple light years away.
Right.
So, they could still phone home as long as there was someone to answer.
Well, if you've got enough of these things, it goes sort of like the von Neumann probe, where,
No, exactly.
you can colonize the entire...
That's what we found in our simulation. Right. I mean, once they're there, how long until they launch another one? And you're like, oh, well, why would they do that? Well, I don't know. Give them 100,000 years. Someone's going to do it.
Well, yeah.
And so that was one of the parameters in our simulation, was how long does it take them to launch another one? And we were pretty conservative. We decided they'd only do it every 100,000 years or something like that. And that's still plenty to effectively create, as you say, a von Neumann machine, this self-replicating series of settlements that quickly takes over the whole galaxy.
All right, Jason, we are out of time. It's been a fantastic interview, and I think the thing that I'm worried about most is if aliens that are colonizing the galaxy in the far future come here and they see Europa and they say, that looks exactly like the place we want to colonize, except the humans have infested it with artificial space sharks. and they move on.
Maybe the Europa report was about their ship.
Yeah. It was great talking to you, Jason. I hope you come back.
All right. Thanks for having me.
John, why's the car back? I thought we'd passed that story arc.
What? The LeBaron's in the driveway.
Well, not quite.
L. Baron. It's missing an E. Wait, the whole car's been altered.
This technology is far beyond human capabilities.
An alien civilization upgraded to LeBaron. Anna, translate that.
He said that his space probe encountered it, and it wants a new carburetor.
Well, I guess I could call Randy.
Please close your rear hatch.
It's got a force field.
All monitored systems are functioning.
The LeBaron's become a technosignature. It's consuming the driveway for raw materials.
Oh, a Von Baron probe. Magnificent.
Thank you.
It's gonna cost a fortune to pour a new driveway.